The first speaker is going to be myself. I'm Santiago Mazuelas. I work in the Basque Center for Applied Mathematics. Today I'm going to describe our work on Minimax risk classifiers. Okay, so to get started, I will start with a sort of a joke. So this is in a machine learning conference, and two researchers that work on supervised classification meet at a coffee break, and one researcher asks the other what he's working on, and one of them says that he works on supervised machines, and the other one says, okay, I work on a totally different field because I work on neural networks. So I think this is kind of funny because it's true. I guess for most of you it's clear that two researchers working on these topics would feel that they work on a totally different field. And it's also shows something interesting about machine learning field is that it tends to be technique oriented more than problem oriented. It's also a little bit strange because the problem these two researchers are working is exactly the same. The formulation is the same. The performance metrics are the same. They use different techniques and they feel they work on totally different fields. And also the techniques they work on are mostly different in the sense that they use different families of functions, but not so, it shouldn't be so different. Right. Okay, so let's get started with the actual talk. Some knowledge gaps that we address in this work is, well, as I mentioned, current techniques for supervised classification consider specific families of classification rules, can be a neural network or a function in a reproducing kernel-Hilbert space. And they use surrogate losses instead of the 0-1 loss, like hinge loss or logistic loss. Also, conventional methods choose the classification rule based on how well that classification rule behaves over a specific training samples. So that makes the algorithms to rely heavily on the specific training samples that we have. And performance is often empirically quantified using test data. So there is no problem in using test data to quantify how good is a classification rule, but it would be nice to also have some tools that tell us how good is the classification rule before we go ahead and use it in practice. Right? The contributions I'm going to describe is efficient classification techniques that utilize original 0-1 loss and consider all possible classification rules. So we don't commit from the start to a specific family of rules. We optimize over all classification rules. And the methodology I'm going to describe utilize expected values instead of the specific training samples and minimizes the worst case performance so that we can obtain performance guarantees at learning. Okay, so let's get started. I will start with the problem formulation. I guess most of you are very familiar with the supervised classification problem. So this is the standard problem formulation. I'm just going to quickly describe to fix some notation. We have pairs X and Y. X, I'm going to call it an instance or an attribute, and Y is the label or a class. And the goal is to obtain a classification rule that just assigns X's to Y's, assign instances to labels. These classification rules, I'm going to consider general classification rules. I'm going to denote the set of all possible classification rules as T. And I'm going to consider all classification rules, even randomized classification rules or deterministic classification rules. So these randomized classification rules choose a label with a certain probability given by this value here. And the way we measure how good is the classification rule is just, well, just counting how many times the classification rule is run, just using the 0-1 loss. Okay. So the goal in this setting is to use some samples, some training samples to obtain one of these rules. And the goal is that the rule that we obtain has a small probability of error, or also called risk or out of sample error, where this probability of error is the expectation of the 0-1 loss with respect to the true underlying distribution that I'm going to call P star. Okay, so this is just notations. So from this problem formulation, it's clear that what we would like to do is to solve this optimization problem. So we would like to find the classification rule that minimizes the probability of error, and we would like to do this minimization over all possible classification rules. We don't really want to choose one family. So the minimum value of this optimization problem is known as base risk, and the solution is the base rule. So base risk is the best possible probability of error, and the base rule is the best possible classification rule. Of course, and this is something that we would like to do, but we cannot do because we don't know the true underlying distribution. So learning approaches, instead of this optimization problem, solve a different optimization problem. And the idea is that these two problems are somehow similar. So general learning approach would solve an optimization problem like this. In this optimization problem, there are three choices that you have to make. So one is which family of classification rules you want to consider, like neural networks or reproducing Hilbert spaces, trees, whatever you want to use, and then which probability distributions you are going to consider. We don't know what is the true underlying distribution, but we need to consider some distributions like the empirical distribution. And after making these choices, the original 0-1 loss often is not tractable. So often we cannot solve these optimization problems with the 0-1 loss. So people tend to use other losses like a hinge loss or logistic loss, etc. Okay, so the most common approach is obviously empirical risk minimization. In this case, the only distribution that we consider is the empirical distribution, and the optimization problem has this form here. We just try to minimize the average loss over the training samples. In this case, the approximation of the original optimization problem with this other optimization problem P is controlled by the choice of the family of functions. If we choose a reduced family of functions, we can ensure that the objective function uniformly approximates the objective of P star. And if we use a general family of functions, we can ensure that the minimum of P is similar to the minimum of P star. So that's the trade-off in this approach. We would like the family to be big enough to have small errors, but we also want it to be small enough so that we don't have overfitting. And in this approach, people call this trade-off a bias variance trade-off. And there is another approach for learning that is somehow a dual approach. So this is a robust risk minimization approach. In this case, we consider multiple distributions, and now we solve the Minimax problem. And now the approximation of the original optimization problem by this optimization problem is controlled by the choice of the set of distributions that we consider, by this set of this uncertainty set of distributions. So here the situation is a little bit it's a little bit dual. If we choose a general uncertainty set, we can make that the objective function here upper bounds the original objective function. And if we choose a reduced uncertainty set, we can make the value of this optimization to be similar to the original value. So here the trade-off is in terms of the uncertainty set. Okay, so these are that's a summary of conventional learning techniques. Now I'm going to describe what the techniques that we propose. So in the techniques that we propose, we, as I described before, we changed the original optimization problem by this other type of optimization problem, but the only choice that we make is the uncertainty set. So we do the optimization over all possible classification rules, and we don't change the loss function, we use the 0-1 loss. Okay, so those are the main differences. So as I said, the only thing that we need to choose is the uncertainty set, and the type of uncertainty sets that we consider is basically what I'm writing here. We estimate the expectation of some function phi using the samples, and then from those estimates, we obtain this set of possible distributions that are all the distributions that have expectations similar to our estimate. And the uncertainty set is also defined using this confidence vector lambda that describes how certain we are about the expectation estimate. This function for which we compute we estimate expectations is a function from examples to real vectors, and these type of functions are usually known as feature mapping. So they are often defined with a one-hot encoding of the label and then using some other functions. If you want to have some examples in mind about these functions, this can be, for instance, polynomials. In that case, we will be estimating the moments of the distribution, or this could be, random features from some positive kernel. So for instance, this could be many sines and cosines in the case that we would be using the Gaussian kernel. Okay, and then as I said, from the training samples, we estimate that expectation. The most straightforward way to estimate that expectation is just using the sample average of the training samples that we have. And the other ingredient to define the uncertainty set is this confidence vector. That we can just use, depending on the feature mapping, we can have a confidence interval for our estimate of the expectation. If we use a confidence interval, then we know that the true underlying distribution is in the uncertainty set with a high probability. And that's what allows us to have performance guarantees. Okay, so before I continue, I think this is a good point. If any of you have some questions about the formulation, you can go ahead and ask, because after this I will show some more technical results. So if you have some questions about the formulation or the setting, that's a good time to ask. No, everything is clear, I hope. Okay, so let's keep going. Okay, so this is basically the setting. The first result is basically a result that tells us how to find these Minimax risk classifiers from data. So basically it says so you can find a solution of this Minimax problem considering all possible classification rules and considering the 0-1 loss by first solving this other optimization problem here. This optimization problem has m variables, where m is the number of components of the feature mapping. You can think of the number of polynomials that you use or the number of sines or cosines that you are using. And this is a convex optimization problem, so it can be solved efficiently. After you solve this optimization problem, you have two things. On one hand, these parameters characterize the classification rule. And also, for free, if you like, you also have the value of the Minimax problem that gives you an upper bound for the probability of error in your classifier. Okay, so this is the optimization problem that you would solve in the learning stage, and in the learning stage, without using any test sample, you would have an upper bound for the probability of error in your classifier. Just another note. So this is some sort of representer theorem, is analogous to the usual representer theorem in some sense. So the usual representer theorem says that we can do empirical risk minimization over a ball in a reproducing kernel Hilbert space because the solution is not infinite dimensional. We know the solution is determined by n parameters. That's what allows to do empirical risk minimization, even considering spaces of infinite dimensions. In this case, this representative theorem is somehow stronger in the sense that here we are doing this optimization not only for classification rules given in the reproducing kernel Hilbert space, but we are doing the optimization over all possible classification rules. And this also tells that even if we do the optimization over all classification rules, the solution is determined by m parameters. In our case, the number of parameters is the number of components in the feature map. Okay, so this is the result that says how to find the MRCs, and I'm going to show what results we have for the performance guarantees. First of all, this first result shows that if we solve these two optimization problems that are also convex and efficiently solvable, these two optimization problems give us an upper and a lower bound for the probability of error for any classification rule. And these bounds are tight in the sense that for some underlying distributions, we have this with equality. In the case that the classification rule is an MRC, the upper bound, as I said before, is obtained directly in the learning phase. So if we are using an MRC, the upper bound comes for free after the learning. And the lower bound would require to solve an additional optimization problem. Okay, so now I'm going to describe the generalization bounds, basically to what probability of error converges as we increase the number of training samples. So the generalization bounds are given in terms of this quantity that is the smallest minimax risk. This would be the minimax risk that you would have if you would know exactly the expectations of the feature mapping. So this is something that you could only do if you have infinite number of samples, but for theoretical purpose, we can try to see how far we are from this quantity. Okay, so the theorem has two parts. In the first part, we have that if we use a confidence vector that is bigger than lambda defining the confidence interval of confidence 1 minus delta, then with probability at least 1 minus delta, we have these bounds. These are basically the previous result I saw. And also we know that the probability of error in the MRC is smaller or equal than the smallest minimax risk and this other quantity. This other quantity depends on the confidence vector and the norm of the best possible parameters. The confidence vector, as we increase the number of training samples, we can is going to converge to 0 at the usual rate of 1 over the square root of the number of training samples. So this says that the probability of error converges to this minimum minimax risk at a rate of 1 over the square root of n, if n is the number of training samples. So this is the first part of the result. And this is valid if the lambdas are valid confidence intervals, but in practice, we might want to be more aggressive and use smaller confidence vectors. Also, because we can be in a situation in which we cannot determine exactly valid confidence vectors. In that case, if we are more aggressive, if we use a smaller lambda, these bounds are slightly worse. So these bounds are only approximately valid. And the tightness of these bounds now depend on how small is the confidence vector that we use. So that basically means that, well, if you use something that is only approximate and the bounds are also approximately correct, And similarly, for the generalization bounds, we also have that the probability of error converges to the smallest probability minimax risk. And here is interesting because this shows that even this bound might be smaller, even if you use a confidence vector that is smaller than the confidence interval. Okay, so this result basically shows to what kind of probability of error these MRCs converge. But now the obvious question is, well, so we know that this converges to this smallest minimal risk, but it would be nice to know how small this thing is, right? So that's basically what I'm going to show in this next result. So this result says that if we use a reasonable feature mapping, in this case, if we use random features corresponding to a characteristic kernel, and as we get more and more samples, we keep increasing the number of random features, that smallest minimax risk I saw before converges to the base risk, converges to the smallest probability of error, and that happens with probability 1 and for any underlying distribution. And the second part is more interesting. So the second part says that if I have an MRC and I choose a confidence vector that tends to 0 at an adequate rate, then the probability of error is going to converge to the smallest probability of error, also with probability 1 and for any probability distribution, underlying distribution. Okay, so those are the universal consistency results we can prove for MRCs. These type of results are known universal consistency results, and the results I'm showing here are analogous to the usual results for other techniques. The main technical difference is that we can do it for characteristic kernels, while it's usually done for universal kernels. And characteristic kernels are a slightly weaker condition than universal. Okay, so now the last part, I'm going to give a short tip for the implementation, and so very quickly some numerical results. In what I saw at the beginning, maybe some of you are wondering how we can do those optimization problems that I saw at the beginning, because in those optimization problems, we need to evaluate this quantity here, and this quantity is a maximum over all possible instances. So in the number of instances in a practical problem is a huge number, so computing this maximum is not really tractable. So the straightforward way to do this, or one natural way to approximate this quantity here, is instead of using all the instances, you use only some, and the instances you have in training, use only some samples of those instances. And this theorem shows that if you use S random instances, and you solve the optimization problems using S random instances, the performance of the MRCs that you would find, as well as the upper and lower bounds, is similar to the performance you would get if you do the maximization over all the instances. And that accuracy in the approximation depends basically on the square root of the number of instances. Okay, and I think just to finalize some numerical results so that you see that this actually works. So basically this shows that the performance we get is competitive with the state of the art, and also maybe somehow more interestingly, that the performance bounds that we get without using test examples are indeed quite tight. So this shows that in these three datasets, the performance bounds, the difference between the performance bounds and the actual probability of error is around 2%. And just to finish, I also want to mention that this code is available in this library in our GitHub. So if you want to give it a try, we will be very happy to, if you do. And also the documentation is also available for all of you. Okay, so I think with this, I will end here. If you have questions, now can be a good time. Questions? Nobody? Yeah, this. You can clap if you like. Aritz has a question. Yeah. Okay, right. So the optimization problems. Well, so this is would say the main optimization problem. This is the one you would solve in learning and would give you the parameters of the classifier and the upper bound. This optimization problem is convex, so there are many techniques you can use to solve it. Indeed, this optimization problem can be also written as a linear optimization problem. So any package that does optimization has it. If you formulate it as a linear optimization problem, the complexity is cubic in the number of, in this M here. We are currently solving it not necessarily with a linear optimization problem, but using a subgradient method. So then using this formulation here and using a subgradient method, basically the complexity depends on how many iterations you run. So the more iterations, the more accurate the solution, but yeah. Yep.
For instance, when you are optimizing in this class of probabilities, I think that is it, you're taking like the worst case, like a bull in some type of measures over the probability space, no?
Okay.
I think that in the literature of robustness, there is a lot of work dealing, for instance, with curval labor. It's like ambassador distance. Here, what is the interpretation of this function that you choose, like the expected value that is close?
Right.
That's my question.
Yes, I had a slide about the related work. So yes, it's a great question. I know you are familiar with this type of work. So one of the technical differences in our work is the type of uncertainty set that we use. As you said, there are multiple uncertainty sets that people have explored, and this is defined in terms of F divergences, or people also use Wasserstein distance to define the uncertainty set. Some other researchers use somehow similar uncertainty sets in which you fix the expectations of some functions, and these other works also fix like the marginals of the distributions. And this other work does something similar to what we do. They fix the distance between the true expectation and the estimate of the expectation. So, and also the marginals. So depending on which uncertainty set that you use, you might have some good properties. So if you use Wasserstein distance, you can also have that the true underlying distribution is inside the uncertainty set with a high confidence, but the minimax problem becomes harder to solve. So if you use Wasserstein distance, these authors also change the loss function to a surrogate loss function. And also they have to constrain the set of classification rules because the minimax problem becomes much harder and they cannot do it in such a generality. Other works that use something similar to what we do, they fix the marginals. So if you fix the marginal, the problem is that the true underlying distribution cannot be inside the uncertainty set because you don't know what is the actual marginal distribution. So then you cannot have these performance guarantees as in our case. I guess this solves Jan. Okay.
Yes.
Okay.